3I/ATLAS isn't just another comet. Based on the anomalies so far, I'd rank it at 4, with roughly a 1 in 500 chance of that happening by accident. Do we officially have the technology to intercept or deal with something alien in the future? No. 3I/ATLAS challenges much of what we thought we knew, and whatever it is, we may never see it again. It began on July 1st when the Atlas survey in Chile flagged a fast-moving object slicing across the sky, a dim, silent intruder, arriving from the direction of Sagittarius, near the dense, star-packed core of our galaxy. At first it looked like a distant comet, a cold wanderer from the fringes of our solar system. That idea didn't last. As more telescopes were pointed at the sun, astronomers realized it was traveling far too fast and to be bound to the sun, a hyperbolic trajectory, an open path inbound from deep space, destined to swing past and never return. But it wasn't the speed that raised eyebrows, it was the precision. Most interstellar objects like Oumuamua or Borisov arrive on steep, irregular paths cutting through the planetary system at odd angles. But this one was different. 3I/ATLAS approached on a path just 5 degrees off the ecliptic, the flat plane where the major planets orbit. As orbital models improved, something stranger emerged. It wasn't merely crossing at a convenient angle, it was set to pass near Venus, then Mars, then Jupiter, in that exact order. A gravity assist sequence uncannily similar to those we designed for spacecraft. That kind of alignment isn't impossible, but it's not what you'd expect from a random interstellar rock. Avi Loeb, the Harvard astrophysicist known for challenging convention, has publicly pegged the odds of such a sequence happening by chance at roughly 1 in 20,000. That number doesn't prove anything, but it's hard to ignore. Then came size estimates based on brightness, assuming a dark, rocky surface. 3I/ATLAS could be up to 20 kilometers across, by far the largest interstellar object ever observed. And yet, during its initial approach, it showed no typical cometary behavior, no jets, no obvious outgassing, just silence. Maybe that's coincidence. The cosmos is vast and probability has room to play. Still, to those watching closely, something about 3I/ATLAS feels off. And unlike Oumuamua, which slipped away before we could react, this time we have a window, a brief chance to study an interstellar visitor. Not after it's gone, but while it moves through the heart of our system, and the closer we look, the less ordinary it appears. From the moment 3I/ATLAS's trajectory was reconstructed, it seemed clear this wasn't just a passerby. It traced a line that felt clean, calculated, and highly improbable. A retrograde orbit, cutting against the planet's flow, fits an interstellar origin, but its low inclination, skimming just above the ecliptic, sets it apart from every other known interstellar visitor. Most arrive at steep angles, diving from above or below the solar plane. 3I/ATLAS instead appears to glide along the same corridor we use to launch probes, where energy is minimized and planetary assists are maximized. Coincidence? Perhaps. Yet each added layer of alignment makes that explanation harder to defend. The flyby sequence, Venus, then Mars, then Jupiter, mirrors gravity assist chains used in interplanetary mission design. If a human engineer had plotted an efficient, no-stop survey of the inner solar system, it might look exactly like this. That doesn't prove artificiality, but it raises an uncomfortable question. Why does a supposedly natural object move with the elegance of intent? Some scientists call these encounters a statistical fluke, unlikely but possible products of gravitational chance. Others aren't so sure. Avi Loeb, urging rigorous open-mindedness, has argued that 3I/ATLAS should be treated as a pedagogical case, not because we have proof of alien technology, but because the pattern of anomalies demands deeper scrutiny. We lose little by asking harder questions, and we might gain everything if we discover what we weren't meant to see. The timing makes it more urgent, as 3I/ATLAS races toward perihelion. It will pass behind the sun from Earth's perspective, entering an observational blackout precisely when cometary activity should peak. Ground-based telescopes won't be able to follow it. Hubble will be blinded by glare. Even James Webb must obey strict pointing limits to protect its optics. To some, that's bad luck. To others, it borders on tactical, as if the object were meant to disappear at the moment of greatest scrutiny. And while that may sound like science fiction, the physics remains. A small adjustment, even just a few centimeters per second of acceleration, would be enough to subtly shift its trajectory over time. If 3I/ATLAS were equipped with any form of propulsion, even passive or ancient, that level of control would be more than plausible. Of course, there's no direct evidence of such a mechanism yet, but we know how to look. That's why Hubble and Webb are watching, dissecting its coma, capturing its light, hunting for chemical signatures that could betray its true nature. Because if this object is what it appears to be, natural, ancient, and purely inert, then it may still teach us more about the galaxy than any comet before it. But if it isn't, if the trajectory we're seeing is not random, but chosen, then we may be staring at something far older and far more deliberate than anything humanity has ever encountered. For weeks, telescopes across the world and above it have been locked onto 3I/ATLAS, trying to answer a question that's older than science itself. What exactly are we looking at? At first, the object was silent. No obvious jets, no tail, no visual cue that it was shedding material. Just a cold, massive core gliding through space. But as it moved closer to the sun, that changed. The coma formed slowly, a faint diffuse envelope of gas and dust. But its behavior wasn't entirely typical. In most comets, solar radiation pushes particles away from the sun, forming tails that stretch into space like a banner caught in the wind. But part of 3I/ATLAS dust stream seemed to bend toward the sun as if heavier grains were resisting the expected force. That alone suggested something unusual in the composition, something dense, perhaps metallic or at least larger than standard comet dust. Then came the spectral data from high-resolution instruments aboard the James Webb Space Telescope and Earth-based observatories like Gemini South. Researchers began to assemble a chemical profile, and what they found was both familiar and unsettling. Water ice, carbon-rich dust, silicates, organic molecule, not unusual on their own. In fact, these are common in many comets. But these weren't fresh materials. They were ancient, possibly older than the sun itself, preserved in a pristine state as if sealed away in a deep freeze for 7 billion years. Some of these compounds showed minimal radiation damage, minimal thermal cycling, and spectral features. That suggested they had never been close to a star until now. Stranger still was the mismatch between brightness and size. The coma glowed unusually bright, yet the inferred nucleus seemed too small for that level of activity. That pushed some researchers to consider another possibility. Perhaps the surface isn't merely reflective, but exceptionally good at scattering light, maybe due to an unusually smooth texture or even a constructed shell. From there, every new data point deepened the puzzle instead of solving it. Contradictions multiplied, chemical, optical, and dynamical clues stacked into a profile that simply didn't behave like the comets we know. Most unsettling of all is its origin. Reconstructed trajectories point back toward the Milky Way's thick disk, a realm crowded with ancient stars and primordial debris, far from the bright nurseries where planets are born. That hints 3I/ATLAS may have been traveling for billions of years before it reached us. It could be a fossil, a shard of galactic memory, unaltered since the dawn of time, or something else entirely, a fragment of design, a long-dead probe, a watcher stirred by starlight. No one is claiming certainty. No responsible scientist is shouting alien without proof. But the discussion is shifting from belief to possibility because 3I/ATLAS is forcing us to confront the limits of our models. And in those limits, we glimpse the shadows of things we don't yet understand. Soon 3I/ATLAS will be gone, slipping behind the sun, lost in glare, unreachable even to our most powerful telescopes. When it reappears weeks later, quieter, colder, dimmer, it will already be on its way out, a silent stranger returning to the dark. We'll be left with spectra, images, and charts, remarkable yet inconclusive. Even with our finest instruments, we may never know whether this was a comet like no other, or something more deliberate, designed to pass close but not too close, to show enough but never everything. Maybe it's coincidence, a natural relic on an improbable path. But if it isn't, if the trajectory, the chemistry, the silence all point to something artificial, then 3I/ATLAS could be the first message we've ever received from a long-gone civilization, or one that still watches quietly. A probe that doesn't transmit, doesn't land, doesn't wait. It simply moves on and disappears like a ghost. And perhaps that's the most unsettling thought. Not that we were visited, but that we weren't the destination, just a waypoint in the dark. Whatever the truth, this moment matters. 3I/Atlas has done what few objects ever do. It made us question what we think we know, widen the aperture of possibility, and ask again, are we truly alone or just not paying attention? If you've stayed with us this far, you're one of the few who are listening. Leave a signal, subscribe to the Space Pulse, and if the mystery, the silence, and the thrill of not knowing speak to you, consider becoming a member. We're building something for you, exclusive dives for those who want to go deeper and drift farther. The sky isn't empty, it never was, and only now are we beginning to see it.